This is page 3 of the network notes, and I'm going to spend time on the IP protocol and then TCP and UDP. And then we'll look at socket programming. So section 2 is the Internet Protocol, or IP, and its job really is to look at addresses and to direct datagrams to their destination address. So it routes datagrams hop by hop across networks, and network routers use something called forwarding tables to determine the outgoing link to send a datagram by. So it receives a datagram and it needs to figure out which network it's going to place it onto next, and it uses these forwarding tables. And so it looks at the datagram, extracts a bit of information from it, and looks it up in this table. These tables are maintained, traditionally at least, by exchanging messages with neighboring routers and figuring out the best way. And so that's, a topic for a full-on networking course, which we're not going to get into here. So the IP header includes either a 32-bit address, and that would be for the IP protocol version 4, which has been around since the early 80s. And an example of that would be something like this: 72.14.192.0. I think that's one of the many IP addresses that Google uses. Or a 128-bit address, and this would be for Internet Protocol version 6. They started designing this protocol in the 90s, and most operating systems had support for IPv6 by the early 2000s, and I think that it started getting deployed slowly, starting at places like universities in the mid-2000s, and its rollout is still going on. So IPv4 and IPv6 coexist side by side, so basically an operating system needs to support both IP protocols to work on current networks, and there's really no end in vision for the IPv4. I think eventually they'd like to get rid of it, but migration has been very slow. So in Canada, there's a Wikipedia article actually on IPv6 deployment, and it shows that Canada as of January was at about 30% of hosts were using IPv6. Worldwide, I think the number is at, well, actually it really varies by country, so from 0 to about 50%. So it's been rather slow. And here's an example of one. Okay, so if we look at the IPv4, it's represented using decimal numbers, and there's 4 decimal numbers, and each decimal number would represent 1 byte's worth of data. So you'd have a number between 0 and 255. Now with 128-bit, they group them into 16 bits, which can be represented with 4 hex digits. And there are 8 of those groupings. So here's another example. So 2607, I believe this is another Google IP address. F8 B0 4003, and then we have a shorter one, C00. So leading zeros can be omitted from the 4-digit hex groupings. Then we've got a double colon, and that represents groupings that are 0. So in this case we've got 1, 2, 3, 4, 5, so there'd be 3 groupings of 4 zeros between those double colons. Now fortunately we don't need to memorize these IP addresses. That would be hard to do. We work better with mnemonics or names, and so DNS, which stands for Domain Name Servers, so DNS hosts translate domain names to IP addresses. And the DNS servers act as a distributed hierarchical database. And so what we've got is at the top of the hierarchy are the root DNS servers. I call them hosts above, server host, whatever. And originally, well, there's 13 named root DNS servers, which is a rather small number, but then they're deployed in clusters, and there's actually hundreds of them spread across the globe. A textbook I was looking at said in 2016 there's 400 of them, so there's probably more now. And so they maintain the lookups for top-level domain servers. So these would be the top-level domain servers, and there would be thousands of these. And so an example of a top-level domain would be something like .com is a big one, .edu is another one, .ca would be another one. And these top-level domain servers are responsible for knowing what servers are deployed. DNS servers are in its domain, I guess, and so then we have a bunch of authoritative, sorry, doesn't fit in the box, authoritative servers. So every institution, whether it's a business, government, university, etc., if they have publicly accessible computers on the internet, they have to maintain an authoritative DNS server or delegate it to someone else that can do that for them. So yeah, so it's actually an example of a very large distributed database. And lastly, so the study of DNS is another big topic we're really not going to get into, but what I just want to summarize by saying is that if you recall, I said that the IP protocol is a best effort protocol, so it'll do its best to route the datagram to its destination, but it doesn't guarantee delivery. So it is said to be unreliable. So if you send an IP packet, it might get to the other end or it might not. So there can be datagram loss. They can actually get duplicated. They can arrive out of order. So I'll just say there can be reordering. And the contents can also be corrupted. So it just it takes care of the routing. The routing's done correctly, the addressing is done correctly, but beyond that it doesn't provide a lot of promises, and that's why you need protocol layers on top of that.